this talk is threshold key storage via fuzzy extractors with applications. Next slide, please. So here's a outline for the talk. So I'll first say a few words about Adva Network Security, which is the company I work for. Then I'll introduce the main topic of threshold key storage and discuss a few building blocks, namely Shamir's secret sharing, threshold pseudorandom oblivious functions, and then we'll see how these building blocks can be used to build a larger construction by the name of threshold oblivious password protected secret sharing. And we'll discuss a scheme, a particular scheme from 2017 by CiarÄ and others. And we'll discuss the pros and cons of this scheme, and then introduce a new proposal for threshold key storage via fuzzy extractors. And then I'll close with some comments for future work. Next slide, please. So just briefly, Adva Network Security is a small company which has recently been carved out of a larger networking company called Adva, which is now being taken over by Adtran. So Adtran manufactures fiber optic communication systems for Ethernet networks, optical transport networks, and Adva Network Security takes care of the security features and certification aspects of these products. Next slide, please. And so the company is also active in various national and European-wide research projects with a focus on quantum key distribution, post-quantum cryptography, and network security. So of relevance to this talk is the AINet Protect project, which has a focus on network security and in particular artificial intelligence tools. And threshold cryptography is one topic being considered in relation to improving network resilience. So that's the background for this work. Next slide, please. So let's get started on the main topic. So threshold cryptography. It's been studied for around 40 years or so and finds use today in decentralized applications. So it's not considered mainstream cryptography yet, although the American Institute NIST has a roadmap towards standardization of threshold cryptography. So what's the motivation? So a single server may be responsible for storing, generating, using a cryptographic key. And in all cases, the server knows all the secret information, which makes it a single point of power or trust, and also a single point of failure or attack. So as a distributed alternative, a TN threshold scheme aims at decentralization among N independent parties, such that any T of them can collaborate to perform a cryptographic operation, but any subset of size less than T can do nothing useful. So the main applications of threshold cryptography are threshold key storage, whereby a cryptographic key is distributed among N servers, such that only T servers need to respond in order to recompute the key. Threshold signatures, whereby there are messages that need signing, but the private signing key is distributed among N parties in such a way that only a subset of size T or more can collaborate to produce valid signatures. And threshold decryption is another scenario whereby the decryption key is distributed to N parties such that only a subset of size T or more can decrypt. Yeah, thank you. So threshold key storage. So what's the scenario? So you want to store a cryptographic key for later use, but you don't trust any single server or device for storing it. So the classic scheme to consider here is Shamir's TN secret sharing scheme, where N is the number of parties and T is the threshold parameter. So secret sharing schemes consist of 3 algorithms: share generation, share distribution, and key reconstruction. So for share generation, we have a dealer who picks a large prime P and creates a polynomial f of x, and where he sets k to be the secret, the constant term k. And the coefficients ai are picked uniformly at random modulo p. And the degree of the polynomial is then t minus 1. So then n shares of the key are generated by evaluating the polynomial on n distinct points, which may as well be the numbers 1 up to n. So for shared distribution, the dealer sends f of I to server I. And for key reconstruction, it suffices to retrieve any t of the n shares from any t servers and perform polynomial interpolation to recompute k. So what are some properties of this scheme? Well, for security, no server learns any information about k. So even if up to t minus 1 of the servers collude or are corrupted. In terms of availability, then only T servers need to be available for key reconstruction. And in terms of robustness, well, reconstruction is possible even if some of the shares are lost or modified. So there are several questions which arise when considering Shamir's basic scheme. So what if reconstruction yields a different key? So it may be that one or more of the shares retrieved at key reconstruction time were modified, meaning that a different key will be computed. Well, there are well-known protocols such as verifiable secret sharing to detect faulty shares, in which case the user could contact a different set of servers to get T-consistent shares to reconstruct the key. Next, so if the servers store their shares for a long time, so it could be the case that an adversary has more chance to break into T of the servers. So if this is a concern, there are proactive secret sharing protocols which can be used for updating or renewing the server shares without changing the underlying secret. So another question is how a user authenticates to T servers at key reconstruction time. So do they use a cryptographic key? Well, no, because secure key storage is the problem we're trying to solve here. Could the user use n strong passwords, one for each server? Well, again, not really, as it's unrealistic for a user to remember all of them. And while using the same single password for n servers is also not a good idea, as if one of the servers becomes compromised, then potentially all of them are. So this question brings us on to the scheme TOPS by Jarecki et al. From 2017. So TOPS here stands for Threshold Oblivious Password Protected Secret Sharing. And here the idea is that the user has one single password, which is used to authenticate to the n servers. And moreover, the n servers learn nothing about the password. So to discuss this scheme in a bit more detail, we need to know about oblivious pseudorandom functions and threshold oblivious pseudorandom functions. So, next slide, please. So firstly, pseudorandom functions. So what is a pseudorandom function? So informally, a family of functions f, depending on some key k, is pseudorandom if fk of x is sufficiently computable, given k and x. Otherwise, it should be indistinguishable from random. And an oblivious pseudorandom function is then a two-party protocol between a user and a server. So the user holds the input value x, and the server holds the key k. And at the end of the protocol, the user learns the output of the function fk of x. And that's it. So the user learns no information about k, and the server learns no information about the input x. So these oblivious PRFs are a useful primitive in many areas of cryptography. For example, oblivious database search, private set intersection, and as we'll see here, password protected secret sharing. Next slide, please. So here's a concrete example of an oblivious PRF, which is at the core of everything that follows. And the protocol is based on a PRF called 2#DH. So what is 2#DH? Well, we let G be a cyclic group of prime order M, and H and H prime be hash functions with ranges L length, bit strings, and G, respectively. Now, for a random key K, 2#DH is computed by hashing X together with H prime of X to the power K. So one expects this function 2#DH to satisfy the definition of a PRF. So easy to compute given the inputs, but without such knowledge, the function is expected to look random. So to evaluate it obliviously, suppose a user has input value X and the server holds the key K. Then the user generates a random integer R, computes H prime of X to the power R, we call this A, and sends A to the server. So the server receives A, simply raises it to the power of his secret K, call this B, and the server sends B back to the user. Now, when the user receives B, he can deblind it by raising B to the power 1 over R. So the R's in the exponent cancel, and in the end, the user has computed the 2#DH function. So this is clearly an efficient protocol with only one round of interaction, involving only a few hashes and exponentiations. And now we come to the main idea, which is that so suppose the user sets the input X to be their password, and K is now a user-specific OPRF key known only to the server, and we set FK of X to be the user secret. So this OPRF protocol can already be seen as a form of key storage. So anytime the user wants to compute their secret, FK of X, they can engage in this OPRF protocol with the server using their password as input. Next slide, please. So yeah, this 2#DH OPRF protocol can be generalized to a threshold setting, whereby there is now not one server, but n servers. We keep the same group G, same hash functions, and the 2#DH function remains the same. So the only difference is that the key, the OPRF key K, is now Tn secret shared among the n servers. So, and it can be evaluated obliviously in a threshold manner. So as before, the user holds X, and now each server I holds a secret share, call it Ki, of the key K. And again, as before, the user generates a random R, but this time sends H prime of X to the power R to any T of the n servers. So the T servers reply with bi, which is a to the power lambda I times ki, where lambda I are the Lagrange coefficients. I just skipped over some of these details. And when the user receives back all the bi's, he just multiplies them all together to recompute compute a to the k, and then the rest of the computation is the same as before, where you raise b to the power 1 over r. So again, this is an efficient threshold scheme involving minimal communications and just a few hashes and exponentiations. So one difference in this threshold version is that the OPRF key K cannot be generated by a single server. So K can either be computed by the user, secret shared and distributed to the n servers, or alternatively, the n servers can engage in a distributed key generation protocol. And the idea for threshold key storage is the same as in the two-party case. So the user sets X to be their password. K is now a distributed OPRF key, and FK of X is the user secret. Next slide, please. Next slide, please. So I can't see the slides anymore. So, yeah, slide number 11. Yeah, thank you. So yeah, we've essentially arrived at the TOPS concrete construction. So this text on the right is taken from the original paper of Jarecki et al. So there's a lot of details, of course, which I haven't mentioned concerning things like session IDs and check values, which are also important parts of the scheme. But anyway, I've tried to convey the main idea of the scheme, which is to use threshold oblivious pseudorandom functions for key storage. Next slide, please. So what are some of the pros and cons of this scheme? Well, TOPS is an elegant, very efficient scheme. However, security depends on user-generated passwords. So in practice, there's always the concern that user passwords have low entropy. And worse than that, it's critical that the user remembers or securely stores their password. So for these schemes, if the password is lost, there is no backup mechanism and the secret is lost forever. So putting threshold notions aside for one moment, so to highlight that this really is a problem in practice, so here's a few news headlines I found about people losing passwords used to protect digital wallets. So just reading from the right-hand side there, the founder of LHV Bank lost the password to his wallet containing 250,000 ETH. Another case, former CTO of Ripple forgot password to hard drive containing 7,000 Bitcoin. And another case, Barbados diplomat lost 800 Bitcoin after reformatting a hard drive. So given this state of affairs, we can ask, is it possible to avoid users having to generate and remember passwords? And equally, do users need to store their private key on a hard drive where it can be wiped or stolen? Next slide. Yeah, so these questions bring us on to the last part of the talk, which is a new proposal for threshold key storage via fuzzy extractors. Next slide. So fuzzy extractors were introduced in 2004 by Dodis et al. And provide a mechanism that, given noisy, non-uniform input, reliably outputs a random string R. So the idea is that users have natural entropy sources that can be extracted and used to generate a random key. So to my knowledge, fuzzy extractors are more commonly used in biometric authentication schemes, but we'll be using them more like in this picture, which was taken from another paper by Dodis et al. So let's start with the user on the left-hand side, who generates some biological reading W, which could be a fingerprint scan, iris scan, voice recording, or something. And then this reading W is then input into a gen algorithm, which outputs a random string R and a public helper string P. So R can be used as a cryptographic key. So in this picture, it's used to encrypt some record. So the ciphertext can be safely stored and R can be discarded. And at a later point in time, when the user wishes to decrypt the record, they take another measurement, W prime, and with helper string P as auxiliary input, it runs the reproduce algorithm to recompute the key R, which can then be used to decrypt the record. And so note that there's no need to ever store R, just some public string P. Next slide, please. So how can fuzzy extractors fit into this threshold key storage scenario? So here's the idea, is that the user takes an initial reading W, runs the gen algorithm to compute helper string P and random string R. P can be stored anywhere publicly. And then the user picks an OPRF key K, which then using Shamir's secret sharing scheme is then TN secret shared, and then share I is then sent to server I, and this key K can now be discarded by the user, and the user secret is then set to be 2#DH, i.e. FK of R here. So at key reconstruction time, this string P together with another biological reading W prime suffice to reproduce the string R. And then given R, the user and servers engage in a threshold OPRF protocol for the user to recompute their secret. Next slide, please. So this is just a more complete slide, repeating essentially the same information, just with some extra details. So things like session IDs, check values, can be included, but no need to go into these details. Next slide. Yeah, so what are the pros and cons of this proposal? Well, some of the pros, so user passwords are eliminated. So there's no need for users to generate, remember, or backup passwords. So the entropy from biometric reading, one would think, would be higher in practice than a typical user-generated password. The scheme is certainly more robust, so users cannot forget something they are. So it could be interesting for high security applications such as cryptocurrency wallet protection. Some of the cons now, well, where does this, so in order to do these biometric readings, must be some hardware coming from somewhere, so that's not desirable. And if it's poorly implemented, then there could be some privacy concerns about user biometric data leakage. Next slide. So in summary, this work has introduced the use of fuzzy extractors to realize threshold key storage without requiring users to remember passwords. It's maybe an interesting approach for online wallet storage. And well, for one topic for future research would be to analyze existing concrete fuzzy extraction mechanisms for practical suitability in threshold key storage and decentralized applications more generally. Yeah, well, next slide. Yeah, and that concludes my talk. So thank you.